The cross product of two vectors is what we're going to use to end up calculating the moments of forces. And in that physical sense, we're going to get that from a combination of a force being applied at a distance and then the direction that it is pointing at. But first we need to talk about how do you actually calculate a cross product. So a cross product is a product between two vectors. It's also known as a vector product sometimes, and it's going to yield a third vector. And that third vector is always going to be perpendicular to both of the original vectors. So here we've got A and B. Our cross product is always going to be perpendicular to the two original vectors. So we're thinking in a 3D kind of sketch here. And then the length of that vector is actually going to be equal to the magnitude of the area that fits in the parallelogram you would draw between A and B. Can be found with this expression, AB sine theta, where theta is that angle between the two vectors themselves, and of course A and B are the length of the two vectors. So that means that A cross B is this vector that is perpendicular to both A and B, and its length is going to be equal to this AB sine theta. The last rule about which direction it goes, because there are technically two vectors, one pointing up and one pointing down, that would be perpendicular to both A and B here, is that it has to follow the right-hand rule. So in order to calculate that, what you do is you take your whole hand and you point your fingers towards A, and then you're going to curl them in the direction that B is from A. And so in this case, when you point your hand sort of down and to the right, and then curl your fingers up and to the left, your thumb is pointing up, which is how you know that A cross B points up instead of down. Now this is a nice kind of graphical, intuitive idea, and as we think about sort of animating this parallelogram, if you change the angle between A and B, as that angle got really, really small, the area in the parallelogram would go to 0, which actually gives us this rule that any vector cross product with itself is going to be 0. And that's because that sine theta disappears down to 0. The maximum cross product is going to happen when A and B are perpendicular, and so that sine theta just becomes a 1 in there because you're taking the sine of 90 degrees. In terms of how we compute this on a regular basis, if we're in a 2D situation where we're looking at A and B down in our plane, it might be really easy to find the angle between them, and we could calculate AB sine theta, and then using our right-hand rule, we know that that cross product would point either straight up out of the page towards us or straight down into the page away from us. But in 3D, we need to come up with a little bit better way to figure out the actual direction of that rather than having to do it all by geometry. There are two different ways I'm going to talk through, and both are mentioned in your textbook. The first one is using the kind of definitions of the cross products of all the different unit vectors. So we can say that, I cross I is 0 because any vector cross itself is 0. I cross j is equal to k. I cross k is equal to negative j, and we could write all these out, but there's a really long set of things to memorize. And so what we do in practice is that we have this mnemonic that we can use to help us remember it. So I draw this on my paper pretty much every time I'm taking a cross product. So you draw I, j, and k in a circle going clockwise. And then you can draw your arrows in to say, okay, this is the direction, clockwise, that these cross products are positive. So I cross j is positive k, j cross k is positive I, and k cross I is positive j. If we go against the arrows in the other direction, though, we know that those are the directions of the negative cross products. So let's look at an example here. We have two vectors that we want to take a cross product of here. Now, one of the nice properties of cross products is that we can go ahead and distribute them out. So essentially, the cross product of these two separate vectors, we can do something that looks very much like FOIL for normal multiplication. So we're going to take that 8i and take the cross product of it with each of these two individual vectors, the 3i and the 2k in the second one, and so on and so forth for each of the terms. Once we have this split into things that have just single unit vectors times each other, what we're going to do is we're going to just kind of multiply the magnitudes together because those are just scalars that multiply by it. And then for each of these, we've got an I cross I, then I cross k, j cross I, and j cross k. We're going to use our mnemonic to remember what these are. The first one, because the cross product of anything with itself is 0, we don't even need to worry about the magnitude of that. Then we've got an I cross k, which if we look at our little diagram here, we see that we're going against the arrow when we go from I to k, which means that this is going to be in the negative j direction, and the magnitude is 16, which is 8 times 2. The next term, we have a j cross I. Looking at our diagram here, again, this one goes against the arrow, so this one's going to be a negative k hat. Our last one here, j cross k, well, that one's with the arrow, so we go j cross k equals positive I, and then the magnitude is 20. The other way of doing this is with the determinant method. And so what we do here is for our cross product, we take our two vectors and we write them out with the first row of the thing we're taking a 3 by 3 determinant of being the unit vectors I, j, and k, and then we fill in the two vectors under that like this. Then we go ahead and just carry out this determinant operation and use that to find the cross product. So let's take a look at this in the same example. Now, if you remember how to take the determinant of a 3 by 3, you can actually do it by splitting it into 3 different 2 by 2s. And so we take the top left element and then the determinant of the 2 by 2 matrix that doesn't include it, and that one gets a positive sign. Then we do a minus on the middle element, and we'll take the first column and the last column of the bottom 2 rows, and a plus on the last one, so that it looks like this when we write it out. Positive I times the determinant of this 2 by 2 minus j, and we put in the 8 and the 3 and the 0 and the 2 here, plus k hat times the determinant 8, 10, 3, 0. And then we can evaluate each of these 2 by 2s. Remember, we take the product along here, and then we subtract off the product along this diagonal. So in this case, that would be 20 minus 0. Here we've got 16 minus 0. And in the k hat, we've got 0 minus 30, which if we look, gives us exactly the same answer as before. I want to end by just giving a summary of the properties of these. We already talked about the fact that any vector cross product with itself is 0. Based on the right-hand rule and what we talked about with the direction, it actually turns out that because A cross B has the same angle between the vectors as B cross A, they're just in the opposite direction. If we flip the order there, we just get the negative. So A cross B is always equal to negative B cross A. Then there's this property that we already talked about with how they distribute. So if we have a vector A cross B plus C, we can go ahead and distribute that out. So that's equal to A cross B plus A cross C. And if we have a scalar in there, we can go ahead and just pull that out or include it in as we want. And so we could pull that scalar into either of the terms, or we could leave it on the outside and multiply it in after we do the cross product. First and foremost, though, remember that when you get to the end of your cross product, you should always have another vector, not a scalar.